Okay, Assalamualaikum and good day, everyone. So today we will continue the next topic lecture for week 7, I think. Okay, this topic is a new topic. So last 2 weeks we have looked into dynamic behavior of process control. So now we will look into one of the control system strategy. We call it as a feedback controllers. So for this topic, we have three main subtopic. We will cover on a basic control modes, where in this topic, I will introduce to you with the proportional, integral, and also derivative controller. And then we will look into PNID control forms and also the block diagram. And last one is the typical response of feedback controller. Okay, I think all of you already have been introduced with what is feedback controller in your first lecture. So this is just to recap. Okay, what is a feedback controller? So feedback controller is where we are measuring the control variable. So basically, in this controller, the corrective action occurs when the control variable deviates or different from the set point. So we take the corrective action when our desired value, which is our control variable, deviate from the set point that we want. So from the blending system that we have learned before, okay, so we have this blending system. We have two input as can be seen from the figure. So okay, where the composition of stream 1 is represented as by x1. For the flow rate, for the stream 1 is represented by W1. And then for the second stream, also same, okay, for the composition, we label it as X2 and the flow rate is W2. And the output of this mixer or of this blending system is only one stream. We label it as X for the composition, and the flow rate is labeled as W. So in this blending system, okay, how do we control our desired value? So the control objective is to ensure that the composition of the outlet at the desired condition. Okay, so if we use a feedback controller, means we are measuring the control variable. So in this case, the control variable is our x. For example, is composition. Okay, so the composition. For example, we want to control this x value. This x value. So okay, for example, we want to control it at 97% composition, for example. Okay. Okay, for example, 7%. So, in order to have this 97%, we have to link this control system with the manipulated flow, which is our manipulated variable is flow rate, which is W2. So we have to put valve here, okay? So this sensor or will measure the composition in this point, at this point, and then it will send the signal to the controller, composition controller, until this composition controller will transmit a signal to this valve, whether it's to be open or to be closed. Okay, for example, if we want to target 97%, okay, but suddenly when the system run and it get 95% this at this point. So what do this controller do? It will send a signal to this valve, so that this valve will control whether it's to open. If it's low, then it will open. If it's higher, then it will close. Okay, so this is this system, we call it as a feedback controller, where we measure the control variable. Okay, in contradiction with this feedback controller, we have another type, which is called as feed forward. Okay, so feed forward, we are measuring the disturbance. So as you can see from this diagram, we have a similar belonging system. So we will put our sensor at the disturbance variable. In this case, disturbance variable is in this flow. Okay, so what we do is when we measure the composition here, if it is not fulfilled for a certain that we want, then it will open or close this valve. So it will not involve with our outlet or our desired value. So this is the difference between feedback and feed-forward controller. Okay, there are 4 modes of controller. This controller, we call it as a proportional. Okay, the first one is proportional. We use P. Okay, and then the second one is proportional plus integral, PI, and then we have proportional plus deviation, PD, and when we combine all PID, we call this proportional plus integral plus deviation. So please remember that we have 4 modes of controller: proportional only, proportional plus integral, proportional plus deviation, and last one is proportional plus integral plus deviation, PID. Okay, as I mentioned just now, the control modes, actually we can divide into 3. The basic control mode, which is proportional control, and then integral and derivative. So from here, we can have that 4 modes of control system, as I mentioned just now. Okay, so before we go one by one for all these 3 control system, so I need to introduce to you this equation. Okay, so this equation represent the error, the error signal. Okay, basically when we control something, of course we want to reduce the error signal to 0, right? So when we control system, we want to make sure that this error is equal to 0. So from this equation, okay, we can see that the error signal is equivalent to the set point itself minus YMT. YMT is the measured value of the control variable, which is equivalent signal from the sensor and transmitter. Okay, so let's look one by one. Okay, first we will look to proportional control. Okay, so what is a proportional control? Okay, by definition, proportional control is the controller output is a proportional to the error signal. Okay, for example, we from the block diagram of a feedback controller. Okay, for example, we have like this. Okay. So this is a feedback system, feedback controller. This is we have. Okay. So here is the output of our controller gain, and this is our error. Okay, for example, this is our KC, our controller gain. So this is our system, any system. Okay, here I just put plant, any system or any plant. All right. So the purpose on doing a control system, okay, we always want to make sure that the error is low as possible. Why? Because to ensure that we get the desired value, right? We want the desired value for our variable. So we want to make sure that the error is low. So how we ensure that this can be happen? By come out with some strategy. For example, proportional control. So this proportional control, okay, actually is a function of error. Okay, any function of error. So we can write like this. Okay, so any outcome or the output of the system we functional we found is a function of the error, because we want to control the error, we want to make sure that it's low. So what we do from the proportional control, okay, from the equation we can see it is proportional with the error. It just a we can write like this, ut is just kc is the control gain multiply with the error. So it's just the simple one where we just multiply the error with kc. Okay, so p portional, this one is just offset. Okay, so from this plan, okay, as you can see here, if we want set the system to have number one. Okay, number one, for example, what happened to the system when it runs, it just can get 0.5 here. So for the controller, okay, 1 minus with the error, 1 minus 0.5, so we will get 0.5 here. So after we control the value, we will obtain 0.5 multiply with k. Okay, so this is how the control system works for proportional. Okay, so it will just multiply this kc with the error to do the correction for this number 1. Okay, so okay, sorry, back to this slide. So from there, okay, basically this kc the key concept behind this proportional control can be strategized into two. First is the controller gain can be adjusted to make the controller output change as sensitive as desired, the deviation between the set point and control variable. And the other one is the sign of kc can be chosen to make the controller output increase or decrease as the error signal increase. So this is two options that we have in order to do the proportional control, as I mentioned just now. Okay, so some controller have a proportional band setting instead of a control gain. So some controller we use proportional band, PB, okay, proportional band. So this proportional band is actually the reciprocal of KC, the controller gain. So PB is equivalent to 1 over KC multiplied by 100%. So this large PB will correspond to a small value of KC and vice versa. Okay, so the transfer function of proportional only control, okay, which only P. So we can write in this form, okay, P for S over ES equivalent to KC, right? So an inherent disadvantage of this proportional only control is that a steady state error or offset occurs after a set point change or a sustained disturbance. Okay, again, the disadvantage of using this proportional, the steady state error or the offset will only occurs after we have changed after the set point have been changed or a sustained disturbance. Okay. Okay, now we move to the next one, which is integral control. So integral control, the controller output depends on the integral of the error signal over time. Okay, the controller output depends on the integral of the error signal over time, meaning to say, okay, the function of ut just now is actually when you multiply k, the constant gain, with some integral function of error. Okay, integral function of error. For example, this is the integral. Okay, integral function. Okay, so this is the concept where it's multiply the k with or for the whole function of error. Okay, so as you can see from this equation, integral control action is normally used in conjunction with proportional control. So or we can integrate with the proportional as well. So this is the function that I mentioned just now. So the proportional, so the proportional is actually the proportional integral actually is the multiplication of the constant gain with the error integral function. So the corresponding transfer function for the PI controller can be written as in the equation 8.9. Okay, so and the third one or the last one, we call it as derivative control. Okay, derivative control. So the function of derivative control is to anticipate the future behavior of the error signal by considering the rate of change. That means the function of ut just now is actually the forecast or the future. Okay, we estimate the prediction of the future error. So we have k in this example, for example, the constant gain will multiply with the error in a derivative function dE over dt. Okay. The concept is where the constant gain is multiplied with or proportional with the derivative error form, where it's actually estimate or prediction for the error. So the control output is proportional to the rate of change of the error signal of the control variable. So we have ideal derivative action. Okay, ideal derivation which given by this equation. Okay. So if you look at here, it's in a derivative function. So this derivative action always used in conjunction with proportional or proportional integral control. So we can actually integrate proportional integral control with derivative. And for ideal PD control, we have ideal and real. So for ideal PD control, we have this transfer function. It can be write like this. But unfortunately, the ideal proportional derivative control is physically unrealizable because it cannot be implemented exactly. So we can say that this ideal is not possible to implement it. Okay. But for real PD controller, the transfer function is given by this equation. Okay. So where the constant alpha typically has a value between 0.05 and 0.2, with 0.1 being a common choice. So in equation 8.12, the derivative term includes a derivative mode filter, which calls as derivative filter, which reduces the sensitivity of the control calculation to high frequency noise in the measurement. Okay, so what's the most important here? You need to understand the basic concept of all three action just now: proportional, integral, and also derivative. Okay. Okay. So for this proportional integral derivative PID, actually we can divide it into three forms. Okay. Which is called as parallel. Wait, parallel. Which is called as parallel, series, and also expanded form. So the parallel form of PID control algorithm we can actually divide into two, which is ideal and real, as I mentioned just now. So let's look at the ideal one. So for the ideal one, this is the expression or the equation. So as you can see here, the PID controller is given by this Kc multiplied with all the derivative function. Okay, so this expression can be write in a transfer function as in equation 8.14 here. Okay, so this function actually can be transformed into block diagram. We call it as a block diagram. So for parallel form, okay, when we transform it into a block diagram, we can see that it's in a parallel form for each each function here. Okay, so we have three functions, so we can write into different box which is parallel to each other. Okay, and this is our control or constant gain. We can put it here. So this is the output, P is the output, and ES is the input. So this block diagram is represent the parallel form of PID controller. The next one is a series form of PID, where it's constructed by having PI element and PD element operate in series. Okay, so PI element and PD element operate in series. So commercial version of the series form controller have a derivative filter as indicated in equation 8.15. So we have derivative filter. So as you can see here, this is the transfer function of a series form of PID, where we have two expression here which belongs to PI or the proportional integral and also proportional derivative function, which we can say that the function here is a multiplication, right? So for in this case, we can say that it is a series function. So when we transform it into block diagram, it must be in series. That means this expression is in one box and another expression is in one box. So this is the output and this is the input. So this is how we plot the block diagram for series form. The next one is expanded form of PID control, which usually used in MATLAB. Okay, we use in the MATLAB. In addition to the well-known series and parallel form, the expanded form of PID control can be write as in expression 8.16. So you can see this is the expression. Okay, so now moving on to the block diagram. Okay, as I showed just now is the block diagram for parallel and series. So the basic on how to actually plot this block diagram. Okay, when we have a transfer function like this, okay, for example, we have a stirred heater transfer function which given as like this, okay, where we can see that there are two expression available here, okay, and from here we can understand there is two input. Okay, we have one input QS and another one is TIS. So this is the input. So we can actually draw like this. So TIS is one input, QS another input. So this input should go into the KC or the constant. So for the expression QS, for input QS is given by this one. So we just put this constant into the box, into the one box, okay. And then another function for constant which put where the input is TI. So we just connect with this TIS with the box and the transfer function was placed in the box. So basically these two expression is parallel. Okay, we're parallel, so it's actually a summation. So what we do is we put this summing junction. We call it as a summing junction. Summing junction where we used to combine several expression. So that is why we connect using this summing junction and put it a plus sign here, meaning that we are going to do the summation okay, for these two inputs. So this input, actually we have one output from this. Okay, so this is the output. So just write like this. Okay, so it just put it like this. So this is how we represent the transform from this expression into block diagram. So as I mentioned just now, summing junction used to any summation of signals. So we can also use a subtraction, indicate with this symbol by placing a minus sign at the appropriate input. So for example, we want the input is minus, so we can replace with minus here. Okay, it's not necessary to have a plus. Probably you can have a minus sign. So the summing junction was used previously as a symbol for the comparator of the controller. So as we already going through all the type of controller, proportional, proportional integral, and also proportional integral and derivative. So this is the summary on the comparison of all the controllers. So for proportional only, okay, it's a simple controller to tune, only KC, and the offset with sustain, disabling, or at set point change. And then for PI, proportional integral, it's a more complicated to tune, especially KC and also integral expression, but better performance than P, and no offset. It's a most popular feedback controller. And last one, PID, it's the most complicated to tune because it has three derivative or three variables, which is constant gain, integral, and also the derivative expression. But it is a better performance than PI. So it also has no offset, and derivative action may be affected by noise. So this is all the pro and cons for each controller. Okay, now we will move to the typical response of feedback control system. Okay, where we want to see the output or the response from the feedback control system. Okay, from this graph, as you can see, when we plot for each controller, if we have no controller, then the curve or the profile is just like this. Okay, no control, the profile is just like this. So the process is slowly reach a new steady state. And then when we place a P proportional control, it will speed up the process response and reduce the offset. So basically, it will speed up a bit. Will speed up if we compare with the no controller, and it will reduce the offset. And for PI, as we can see here, it will eliminate the offset and the response more oscillatory. Okay, the PI will start to oscillate compared to proportional. And last one is PID. It will reduce the degree of oscillation and the response time. So PID will reduce the oscillatory or oscillation and also the response time. So this graph is important so that you will understand better on what we have learned for today's lesson. So I think that is all for today's topic. So I hope that all of you can look at this video and can be your future reference if you want to study or whatsoever. So that's all for today. Thank you for listening and for watching this video. Okay, have a nice day, everyone. Bye.